Welcome once again to the Simpkins Physics Corner. Today's topic for AP Physics 1 is Atwoods and FBDs. What is an Atwood machine? Well, it looks like one of these puppies right here. If you freak out at that math, don't worry. I'm going to take you through this problem-solving approach because Atwoods are, they look crazy at first, but when you understand the ideas behind the Atwoods, it's a little more manageable. So that's my job today, is to break this down for you here. All right, so don't panic. Mr. Simpkins is here for you. Let's see what we can learn about Atwood machines. Let's not forget everything that we've gone through already. Newton's third law says that for every force, there's an equal and opposite reaction force, or that forces occur in pairs. And so the definition, by the way, of an Atwood machine is just something that, it's kind of like you have a pulley here, and you have strings and some masses hanging on them. All right, so when I say Atwood machine, that's what I'm talking about. It's just, a rig of a pulley with two masses. Sometimes we put 3 or 4 masses on them, but basically we have a pulley with masses hanging on either side. Now, as you can imagine, if these objects were of equal mass, then we could expect the system to be in equilibrium or at rest. All the forces would be balanced. All right, but let's consider the types of forces we have here. We have the force of gravity pulling on mass 2, and we have the force of gravity pulling on mass 1. Now, the thing where people get confused is you're like, well, both forces are down, right? But how are they counteracting each other then? Well, of course, they're tied together with a string. So let's focus in on mass 1. The Fg, force of gravity on that box, is down, but the string is pulling it up. And so the up force, we'll call this Ft for force of tension, is equal to the Fg on mass 1. And then if we come over here, we have that string is holding this one up. Ft is pulling Fg up. Now there's a rule that we want to remember when we look at all these problems. And here's the rule. The tension is constant throughout a string. And the reason that has to be true is because of Newton's third law. Remember, we said it is impossible in a tug of war to register a different force over here than it is over here, because Newton's third law, for every action, there's an equal and opposite reaction force, or forces occur in pairs. All right? There is no possible way that, like, for instance, this guy couldn't pull with 300, and these people over here only experience 200. That would be a magical dissipation of 100 newtons of force, which is not a thing. All right, so that's not a scenario, and so that's why this rule of the force of tension must be constant throughout a string is the rule that it is. Now, what if these masses were not balanced? Well, then we would not be in equilibrium. And remember, anytime the sum of the forces are not balanced, that's going to cause a mass to accelerate. Or in this case, for today, a system of masses to accelerate. So before we jump in too hard, let's go ahead and draw some forces. So for this scenario, I'm going to say that this is the heavy boy right here. This one's heavier, and M1 is lighter. Okay, and in order to indicate that, I'm going to draw a bigger Fg on the mass 2, all right, and I'll just draw an Ft like this. Now, I'm being very particular about the length of my arrows because we know that vectors tell us about the magnitude and direction, and you'll notice that if M2 is heavier, just imagine what would happen. M2 would fall down. Sorry, my hands are backwards as far as the graph goes. M2 would fall down and M1 would move up. If this one's heavier, it's going to pull down and it's going to win the tug of war. All right, so that's why this Fg down on M2 is bigger than the force of tension up, right? Because if you can say, well, isn't the string holding it? Well, yeah, the string's holding it, but it's not holding it so much that it doesn't move. And if it's not moving, if it's accelerating down, that must mean that the biggest force is down by Newton's second law, F equals ma. Okay, let's keep going. Now, as we move over to M1, what we know for our rule for strings is that the Ft, the force of tension, has to be constant throughout the string. So I didn't do a great job, but I did my best. Here, let me just make this one a tiny bit longer. I did my best to make these two force of tensions arrows the same length. Why? Because of that rule. The force of tension is equal throughout the string. Now, if M1 is lighter than M2, then it's going to accelerate upwards. And if we have an upwards acceleration, that must mean the direction of the largest force on that object is up. And what does that mean? That means that the force of gravity down on M1 is going to have a shorter arrow than the Ft. Okay, so let's summarize here. If M2 is heavier, it's going to pull harder on the system than M1 is pulling this way, right? So it wins the battle. And so the resulting motion would be acceleration down for M2 and acceleration up for M1. And if we look at these free body diagrams here, that would be the thing that we would predict. We'd say, oh, because the downward force on M2 is larger than the upward force, we expect it to accelerate down. And because the upward force on M1 is larger than the downward force on M1, we expect it to accelerate up. Now, the people will get confused because of these up and down things, right? But when you use an Atwood machine, I can do this. I can define this direction as positive. What? Okay, yes, you can do that, all right? You can define that direction as positive. And the reason you can do that is because imagine if, well, I'll actually unpack it in a little bit, all right? But the reason we can do that is because of the string rule, all right? We know that the force of tension is constant throughout, and we can define the system of the two blocks. We can define positive as anytime that system moves in this direction, which looks kind of funky. But let's put some numbers to it to see if we can solve for something like this. So here we have a 3 kilogram and a 5 kilogram block. That means that this force of gravity on the 5 kilogram block is going to be larger than the force of tension. The force of tensions have to be equal throughout the string because of our rule from Newton's third law's implication. And this FG has to be the smallest one of all because it's the least pull that we're going to get. Now, when we look at this, we can consider it as a tug of war. I'm going to define this direction as positive. And what we can do is we can write a sigma F equals ma expression for the system. We can write a sigma F equals ma expression for each individual block. And depending on what information you get and what type of problem you're doing, those two strategies are going to be appropriate at certain times. So when it says what's the acceleration of the system, I would encourage you to always attempt to solve this as a system. So let's just kind of take stock here of the sigma F equals ma expression. All right. Now, for the system, what forces must we account for? I'm going to call this mass 1, and I'm going to call this mass 2. All right, so I would label this Fg2, and I would label this Fg1, because the force of gravity on mass 2, force of gravity on mass 1. And we know that this Ft is the same as this Ft. Okay, now, let's go ahead and sketch this out. Look at all the forces tending in the direction that we've defined here as positive, or the ones that are going in the negative direction. Well, Fg2 is going in the positive direction, so that's the first one I'm going to start with. Fg2 is going in the positive direction. Are there any other forces moving in that same direction? Well, look, if we follow along, isn't Ft, and I'll even call this Ft1 and Ft2. We know they're the same, but I'm just follow with me here. Ft1 is pointing in that positive direction that we've defined, so I'm going to say plus Ft1. But look in the other direction. Opposing this motion is going to be, see positive is this way. Ft2 is the opposite direction of our positive, so minus Ft2. All right. And then if we look at the other force opposing our motion, it's going to be minus Fg1. Now, this is called the explosion, or you kind of blow out the forces from sigma F. Remember, sigma F means sum of all the forces. And you may question why I'm using a minus sign. Well, that's because I'm adding a negative force, or I'm adding a force that's in the opposite direction. And so this whole side of the equation comes from using our free body diagrams to express what all the forces are, and we've defined this problem as acting on our system. Now, what is the mass of the system? Here's where you got to be careful how you define things. Our system includes both blocks. So what is the mass of our system? The mass of our system is 8 kilograms, 5 plus 3. And then, of course, we have acceleration. So let's go ahead and see what happens. We've already mentioned that Ft1 and Ft2 are equal. And what happens if you add Ft1 and you subtract Ft2? Well, this right here would go away because you'd be adding tension and subtracting it away, so it kind of cancels out. And this is the beautiful thing about the systems approach, is that a lot of times our forces of tension will cancel out if we do our math right. And so that just leaves us with this. Fg2 minus Fg1 equals 8 times A. We're getting close. Remember our definition of the force of gravity. Wait, force of gravity. The force of gravity definition is m times g. G is our gravitational acceleration. So really what we're looking at then is m2g minus m1g equals 8a. And if we do a little factoring here, we can factor out the g. So we say m2 minus m1 equals 8a. All right, and we're getting pretty close here. Remember, we're trying to solve for a, the acceleration. So why don't we go ahead and isolate it by doing some algebra here. So a is going to be equal to g. Now, some of you will get triggered at this. I used to. I'm going to round it to 10. We know g is 9.81, and you probably know all the decimal points. But I'm going to round it to 10 to keep the math easy because I'm focused on the ideas today. So we're going to call g 10 meters per second squared. I know, trigger warning. And then m2 is 5 minus m1 is 3 over 8. And so what do we have here? That's going to be 20 over 8. And 20 over 8 is going to get us our acceleration. Sorry, my slide skipped on me here. Is going to get us the acceleration of the system, 20 over 8. That's going to be 2.5 meters per second squared, and it's in the positive direction. Now, quick note, if you ever get a g that's bigger than 9.8, you did something wrong, okay? Why? Because if I just drop a block, that's how fast it's going to accelerate. If I tie another block to that block, there's no way it can go faster than gravity would accelerate, right? So just a little side note. But here, the acceleration of the system would be 2.5 meters per second squared. The next one, what is the tension in the string? Remember earlier I said we can write a sigma F equals ma expression for the system, or we can write it for an individual block. And different scenarios will make different strategies appropriate. Here, let's go ahead and just focus on this block right here. And the reason I need to do that is because if I use the system's expression, the tensions cancel out. You can't solve for tension if it cancels out, right? So let's look at this block. The answer, ladies and gentlemen, is always sigma F equals ma. You think I joke. The answer is literally always sigma F equals ma, or at least it always starts from there, okay? Sorry, my slides are skipping like crazy. So if we look at that block I've circled in purple, it's going to be influenced by FG2, and it's going to be influenced by FT, and we have our ma on this side. Oh my goodness, this slide skipping is just going to make me throw my computer. Okay, so FG2 is going to be M2G minus FT equals, all right, now, careful. Earlier, we said that M is defined as the system. That's why we used 8 kilograms. But we're no longer looking at the whole system. Now we're focusing in on mass 2. And so when I use this equation here, I'm going to put there mass 2. And then acceleration, actually, we already solved for. We know that that's 2.5. Okay, so not a far stretch here. My goodness, if these slides, not a far stretch here to see how we could do the algebra. All right, so I'm going to skip a few algebra steps, as my slides like to skip a few steps ahead. But let's see, if I added ft to the right side to get rid of the negative, if you will, then that means I would have on this side left over, I'd have m2g minus m2 2.5. And then, of course, if I wanted to do some gross rounding, I would do m2 times 10 minus m2 times 2.5. And of course, we could factor out the m2 of that. So we could say m2 is 5 times 10 minus 2.5. And that would be, let's see, 5 times, what, 7.5? I don't feel like doing that in my head, so let's drop it in our calculator. 5 times 7.5. That would be 37.5 newtons of tension. And remember, force of tension over here is the same as the force of tension over here. All right, so that is a little bit of a overview of how you would use sometimes the systems approach starting from sigma F equals ma, and sometimes the individual masses approach with F equals ma. I only have 2 minutes left, so let me just leave you with this thought. Sometimes they'll give you gross problems like this, and people get confused, but let's not be confused, because remember, it's all about what direction you define as positive. So one way to think about this particular problem is not that gravity is pulling down and causes the block to move sideways. That's kind of crazy, right? What if I think about sideways gravity? What? What? What are you doing, Mr. Simpkins? Okay, well, just look. This makes sense. If we define this direction as positive, we can use the same strategies we used for the other one. Remember, the most useful way to solve these most of the time is to first try the systems approach. So in this system, this is block B and block A. We would have the force of gravity on block B down, and we would have the force of tension up. But what happens? Oh, this force of tension is also in the system. It's equal to the other force of tension and therefore cancels. So really the only force, if we assume this is frictionless, which we will because it's physics class, we like to do that, the only force actually then that doesn't cancel out is FGB. But the thing that people will trip up on is they'll forget that they're writing this as an expression for the entire system. And the entire system's mass is 12 kilograms, 2 plus 10. Okay, so then, and then here's where you have to be careful too. Fg on block B, this would be mb times g equals 12a. All right, in this case, it would be 2 times, I'm going to be gross and round it. I know, I'm sorry, I apologize. All right, and then we divide both sides by 12 and get our acceleration. Okay, so 20 over 12, I ended up having time to solve this problem anyway, is 1.67. Take some time to stop, to come back, to look at these slides, to chew on this a little bit. You notice that this was an expression for the system, right? And I didn't bother writing the FTs in here because I know they're always going to cancel out for me anyway, all right? But take careful note that this over here is the mass of the block that gravity is actually pulling on, and this is the mass of the system. Mr. Simpkins in the Simpkins Physics Corner, I'm out.